This is the Brookfield Viscosity measurement instrument. It is a very excellent and very precise mechanical type device, equipped also with a precisely controlled motor that can change speeds, and it measures the viscosity of a fluid that is placed underneath. Let me turn it on and show you how it works. First, very important that it be absolutely on a vibration-free level surface, out of the range of any air currents, particularly anything that could possibly come in and affect the measurement while it's being made. First, to turn it on, it's a simple switch, and you'll start to see the dial rotate as we progress through the 8 speeds of this particular model. That's a half an RPM, 1, 2.5, 5, 10, 20, 50, and 100. Now, the different speeds are important, and depending on which spindle that you will use, that'll help you decide which speed you want to use. Now, the way it actually measures the torque required to spin in the particular type of fluid that you're putting underneath is through a series of spindles. Now, these spindles attach underneath here onto the motor. And once they're immersed in the fluid, they then will measure the amount of drag on that spindle, and on the red needle on the dial on top will indicate a certain percentage of torque. Once you have that number, you can then take a very simple equation where you'll take that direct measurement of torque times a particular factor, and that will then give you the measurement of centipoise, which is the actual measurement of viscosity. For convenience, our particular model is an RV series, so we'll put our chart right there. Also conveniently, since you have several variables, not only the spindle size, but the spindle speed as well, and temperature is always a factor, or temperature of the fluid. They've provided you with, it's in the back of the manual, these very, very handy test reports, which I've been using as well, to record your data and to also check on calibration. To give a demonstration of how it reads the viscosity of different fluids, first I'll remove the spindle. The spindle can never be installed unless it is already immersed in the fluid that you're measuring. Now, I can use any one of these. This correlates with this right here. This is spindle 1 through spindle 7. And this is spindle 1 through spindle 7, showing the spindle, showing the spindle speed that you set, the factor that you have to multiply by, and that will give you your viscosity measurement. Now, even the thinnest of fluids, like even water, has a viscosity reading. And sometimes people will look at fluids and think that the darker the fluid, the higher the viscosity should be, or the thicker the fluid is, in simple terms. Well, let's do a simple test here. Get rid of our water. I'm going to take sample 1. These are 3 examples of oils used in industrial vacuum pumps. These are both new oils. This is formulin oil, which is synthetic oil. This is a more petroleum-based oil. And this is used oil from an older vacuum pump. We'll take the first one, which is clear. And for purposes of our experiment, I will use Spindle 2. Now, one of the things that they made very clear in the instruction manual is that you can trap air underneath these spindles, and that will affect the reading. So when you submerge the spindle, you do it at an angle, so this way you don't trap any air underneath. You keep it submerged, bring the head down, and connect it. Hand tight. You don't have to torque this up. And then it needs to be submerged to a certain depth. Now, on every spindle, there is a notch right here. That is the immersion notch. And once you have the spindle in place, you lower the spindle to the meniscus. It comes right around the notch. Center it respectively, and turn it on. Now, for purposes of our demonstration, I'm going to set it to 1 speed. I'm going to set it to 10 RPM and measure this fluid. Now, once you turn this on, you need to at least give it several complete revolutions for the measurement needle to stabilize. And once it's stabilized, you can take that reading. Now, it might be difficult to take that reading as this is spinning. So, they've installed a clutch. There's a pin on the back here that you push down with your hand, and it will lock the needle in place where it took its last measurement. Hold on, I'll catch it as it goes by. There. And in this case here, we have a measurement of 1, 5, 6, 7, 8. We have an actual reading of 8. And if we were to convert that, this would be spindle 2 at 10 RPM times a factor of 40. So that would simply be 8 times 40. Would give me 320 centipoise measurement of viscosity. Now, we're going to use the same spindle and the same speed for each of the sample fluids. Okay, after you thoroughly clean the spindle from its last use, getting all the oil off of it in an alcohol rinse, we're going to try the second sample. Now, the second sample has a darker appearance than the first sample, making you think it might have a higher viscosity. Well, we'll see. I like to give it at least 4 to 5 revolutions before I We're going to lock it in place. And 4. This measures 4. Again at the same speed. Spindle 2. 10 RPM. Factor 40. So 4 times 40 is 160, which is certainly a lot less than the sample 1 fluid. Now we'll move on to the third sample. Now, in this third sample, this is the used vacuum pump oil that is obviously highly contaminated with different particles, which will probably give the base of this oil a thicker consistency, but we'll see what happens. Again, we're using the same spindle, same depth, same size beakers as well, and the same speed, 10 RPM. Okay, we've given it some turns. We'll lock the clutch and take a look. And we are at 19. Times 40 equals 760. So our third sample has a viscosity of 760 centipoise. And as a review, our first was 320, our second was 160. So this is the using a comfortable term, this is the thicker fluid with a higher viscosity. For this fourth and final sample, what we're going to use is a certified viscosity standard. These are available through a number of vendors. Brookfield has an entire series of different viscosity standards that you can use. This particular one that we're using has a viscosity of between 2026 and 1335 between 20 degrees C and 25 degrees C. Our fluid is somewhere around 22, so our viscosity measurement should fall somewhere between this range. Now, this is very pure, so it's important that you try to keep it away from any contaminants. Now, I've put it in this little beaker right here. For this particular final test, we are going to change spindles, and I'm going to go to spindle 4. 1, 2, 3, 4. You know you have the right spindle because right on top of the spindle there is a number scribed for each spindle, and this is spindle 4. Now, we lower our head. Okay, hold on. Now, let me make sure this is, oh, it should be submerged. Oh, there it is, right there. There's our mark. Measure temperature. And we will place this right there. Now, according to the manufacturer, it's important to note that at very low torque measurements, there is a degree of about 10% inaccuracy. So, a lot of times, it is better just to step your way through. And we're going to pick, let's say, for purposes of our measurement, we'll go back to 10 RPM, similar to what we did with these other samples as well. We'll give it a chance to spin. Lock it. And 9.9, almost 10. We go to the chart. We are now on spindle 4 at 10 RPM. So we have a factor of 200. If we were to put in, it was just about 10. 10 times 200 is 2,000, which is approximately now. How about we go up a little faster just to see the uniformity of the fluid. Now, why don't we go up a little faster and see if we can see the uniformity of the fluid. I'll lock the brake. And I get just about 20. That's 20 at 20 RPM. So, spindle 4, pardon me, yeah, 20 RPM. 20 RPM has a factor of 100. 20 RPM times 100 equals 2,000. So, through the range of our readings here, it has a consistent viscosity. That is known as a Newtonian fluid. In other words, you can change speeds with the fluid, but the viscosity will not change. What's admirable about this instrument is that other than an electric motor with a speed control, it is entirely a mechanical device. This reading is entirely obtained from a mechanical beryllium spring measuring torque, and it is very, very accurate. Probably as accurate, if not more accurate, than some of the current models of this equipment. It's very dependable.